We're back with separable equations, and I want to do another one from the book. Let's see, this was u as a function of t. This was, let's see if I can remember it. It was 2 plus 2u plus t plus tu. So this is a great example of algebra before calculus, ABC, as we say. And you might think, oh, this is actually very nice. It's just a sum of 4 things, and I'm just going to use subtraction to move some across and subtract and move others across. But let's look over here. The way I have of separating out the du and dt is products and quotients, is to multiply by the dt. So if this isn't a sum of things involving t and u, that's not going to help me. What I need to have is I need to be able to write this as some function of t times some other function of u. Or divided by. Times or divided by. Those are going to work. Sums are not actually good. So can I rewrite this in this way? Well, this is a good time to pause the video if you really want to figure this out for yourself. Can you rewrite this purely with algebra as a product of something involving only t and as something involving only u? Okay, you're back. Good. Glad you figured it out on your own. It's grouping. This is going to be 2 plus t and 1 plus u. It's exactly set up so that it groups tu and then a t separately and then a 2u and then a 2. That is something I can separate. So now du over 1 plus u is dt over 2 plus 2 plus t dt. And now I integrate both sides. So do algebra to get it ready if necessary. Separate, integrate, and celebrate. Something like that. Now here, let's see. Let's do this one first. This is just 2t plus t squared over 2 plus c. I always put the plus c over with the independent variable because we're going to want to, if possible, we're going to isolate the u and solve for the u. And we don't want to have any extra clutter over there. So this one, we're going to need to do a u sub here. X equals 1 plus u. So dx is du. And that's pretty much it. So this becomes integral dx over x. That's ln absolute x. And so this is going to be another one of those finicky examples. I'm going to try and do another one without the finickiness, but I like this algebra for calculus bit well enough, and we did this in class, that I wanted to do this. So we strip off the ln. That's a plus c. Let me call it a c1, just like we did before. And then we strip off the plus or minus, and we move the plus, and we move the e to the c down. And we get the same thing: plus or minus e to the c1 times this more complicated exponential. And then x, we need to change that back to 1 plus u. So 1 plus u equals plus or minus e to the c1 e to the 2t plus t squared over 2. And this thing, I just package up as a c. Oh, wait a minute. Can c equal 0? Is that okay? You can't really see that. C equals 0. Is that okay? That's what I'm trying to say there. Well, we have to go way back. Can 1 plus u equal 0 here? Let's see. If 1 plus u equals 0, that means u is constant, just the constant function minus 1. Does that work? Well, let's see. That would make the right-hand side 0. And yeah, a constant function has derivative 0. That would make the left-hand side 0. Check. It does work. So what that means is, yes, that is going to work. And that typically happens, is when you check that separately, it does turn out to work. And then I just have to subtract 1. So, in a lot of ways, that was just kind of a more complicated example of the stuff we saw in the first example. Now, let me see how much time we have. Oh, plenty of time. Let me just give you another one that's actually a rather simpler example without the finicky thing. Let's say dz dt equals e to the 2t over 4z cubed. Now, it's a quotient of things already a quotient of a function of t only and a function of z only. And so that's going to be easy to separate. We just cross multiply. We integrate both sides. Antiderivative of 4z cubed, z to the fourth. Antiderivative of this guy. We could do that as a u sub. It's not too hard to do it as sort of a guess and check. Antiderivative of e should basically be e of the same thing. But if we took the derivative of e to the 2t alone, then it would just be, it would give us a 2 out, and we need to cancel that out. Again, you can do it as a u sub if you want. Now I put a constant over here. I don't know if I mentioned before, you don't have to put arbitrary constants on both sides. Because if I put an arbitrary constant over here, like if this was like c2, then I could just move it over, and then that would be c minus c2. Well, that's still just an arbitrary number. All it's saying is that these guys have to be the same, except they could just differ by a constant. The simplest way to do that, to say that, is just not even worry about that, and just leave it alone on one side. And then we just have to solve for z. In this case, it's pretty easy. Plus or minus the fourth root. That's plus or minus because anytime you take an even root, you need a plus or minus. And that's going to be our solution here. Now notice here, you might wonder, let's see. It looks like maybe, I'm not sure if I could get 0 out of this. Fourth root of this variable thing, that's maybe not going to give z equals 0, but you know what? Already, z really couldn't have been 0 right at the start. That's not something I forced into this situation. If this was the correct way to write the equation, and this was what's given to me, then z is not going to be 0 right at the start. And so there's really not a worry comparable to what we had in the other version. We never divided by a variable, we just cross-multiplied. We can be really pretty sure that that's the full solution to our equation. Okay, that's 3 examples. That's as much as I did for anybody in class, and that should be a good start for you guys.